Put up our checklist there. What are the forces acting on the hanging mass? Let's see. Not worrying about friction. Tension's done. There's no other weight. Normal force.
No, because there's no contact.
All right. So I just have these two right here. Which way will the mass accelerate? The hanging mass is going to accelerate upwards? Is that what you, did I interpret that correctly, Savannah?
Yes.
So when I remove this, that's going to come up.
No,
You think it's going to go down?
I don't know.
It's one of those two. But when I let go of, when I remove this from blocking this, which way is that mass going to go?
We know it's going down because you had to place the block there, but.
Yeah.
So like how though?
How much, what?
How? Like, cause the mass weighs less than the.
Well, we'll get to that in a moment. So, but you're making an argument the fact that it's going to fall.
Yeah.
And Savannah, you're not sure which way that's going to go? Anyone else? So just the voice of Caleb and non-committal?
Is the string underneath that bigger weight?
The string is attached to the card itself.
Okay.
So, well, we can do a quick demonstration here. It looked like it went down. So if it's going to accelerate downwards, because it starts at rest, if it were in equilibrium, it wouldn't move at all, because it starts at rest, and if acceleration is 0, velocity won't change, so it'll stay at rest. But it does move down, it does accelerate downwards, so which one of these is going to be bigger?
Wait.
Yeah. So I know that F equals ma. And my total force here is the weight minus the tension. It's going to be equal to that hanging mass times whatever its acceleration is. It's just F equals ma for that thing hanging on the end.
Does that say weight minus total force?
Weight minus the tension. Yes. Oh, that I made down positive there. If you made up positive, then it'd be negative W plus FT. All right, so force diagram of the cart.
Oh, the weight of the cart doesn't matter that much because it's frictionless, right? Because it can't resist. That makes sense.
It also, which way is the cart going to accelerate?
On the diagram that way.
All right, got a finger pointed that way. Angel, you're pointing the other direction. And fight.
It's accelerating toward.
Oh.
'Cause
Part of the problem. Were you looking at that and you were looking at this?
The moving the car.
Yeah, okay. That's backwards from what I did here, so you're both right. It is gonna move to the right here, it is gonna move to the left here. Down is still down. In this drawing, which way will the cart accelerate? Okay, it will accelerate that way. All right, what are the forces acting on it? We got the checklist here. We are assuming that friction is negligible, although on this card it might not be, but let's assume. The friction's gone.
Normal force
Going,
from the card going up.
on the cart?
Yeah.
All right, so I got a normal force going up.
The weight is maybe acting on the wheel, I would say, or no?
You want to break the cart up into wheels and the rest of the cart?
Yes.
That's a path to insanity. I refuse. Let's think of the cart with the wheels, that's one whole thing.
Weight acting down.
Yeah, weight's acting down on the whole thing. That normal force is acting up on each of the four wheels, but we're just gonna lump it into one normal force acting up. I've got one other force acting on it.
Tension
Acting,
towards the right.
yeah. So I have a tension acting that way. Now, if I threw the string into that, there'd be a tension acting this way, a tension acting down, and some sort of normal force acting that way. But all I really care about are the cart and the hanging mass. So if this is going to accelerate to the right, well, I have only one force that's horizontal. So I would have tension equals mass of the cart times acceleration. I do point out that those accelerations are the same. If this is an ideal string, it's not going to stretch. It's not like the mass is going to start falling before this starts moving. There's not a slinky there. So they will accelerate, have the same magnitude of acceleration. Can't be the same vector because that's accelerating downwards and that's accelerating that way. But the directions, the magnitudes are the same. So I know what the tension is. There's a couple ways to solve this, and this depends upon your math background, whether this will seem bizarre or familiar. These are my two equations right here. These are called the equations of motion. I'm just going to add them together. I have weight minus tension plus tension. Well, my tensions cancel out, and all I'm left with is weight. Over here, I have the hanging mass times acceleration plus the cart, mass of the cart times acceleration. So this is hanging mass. Let's differentiate here. This is, I do need to differentiate these two weights. So that's the hanging weight is equal to the mass, hanging mass times acceleration plus the cart, mass of the cart times acceleration. How do I find weight? What is the formula for weight?
Mass times the acceleration due to gravity.
All right, so we got the hanging mass times G is equal to hanging mass times acceleration plus mass of the car times acceleration. Let's plug a jug. This is 0.05 times.
9.8.
Good enough for here? And that's going to be equal to 0.05A plus 0.5A. So I have 0.05A plus 0.5A, what does that equal to?
0.55.
So 0.05 times 9.8 is 0.49, I think. Let's see, if it were just 5, it'd be 49, so yeah, 0.49, got it. And that's an A. All right, so my math problem, 0.49 is equal to 0.55A. How do you solve it?
Divide by 0.55.
Is Caleb right? Was Caleb chosen as one of the spokespeople for today? Do you support him?
Yes.
Yes.
Got 2 people supporting you. The rest of them, they're still unsure. Whenever you're solving for an unknown, you gotta peel away the layers. This is where my unknown is. I gotta get rid of that 0.55, so I undo it. Well, what's going on between 0.55 and A? Multiplication, and you undo multiplication with division. So 0.55, 0.55. And so A is that fraction there. This is division. So 0.49 divided by 0.55, which is 0.8 something. 89.
Meters per second.
All right, before we actually use this to predict how long it's going to take, let's recognize what's going on here. We have F equals ma. That's the heart of this. The force that's driving all of this is the weight of this hanging mass. That's the force that's driving it. The weight of this is acting up and down, or acting down, normal force acting up, but the car is not accelerating that way. If this had no weight, that's not going to move. It's getting moved because of this. So that weight of the hanging mass is the entire driving force. And then it's equal to the mass times the acceleration. Well, the total mass that's moving is the car plus what's hanging. That total mass is moving. So what we have there is my hanging weight is equal to my total mass, everything that's going to accelerate, times acceleration. This is F, that's my total force, is equal to mass times acceleration. My total mass, and everything has the same acceleration. Questions up to here? Still don't want to use the marker on this. All right, so now I'm going to make a prediction about how long it takes this thing to go. First off, I want to make that string as, I want to make this string, this fishing line, as horizontal as possible, because I am assuming that tension is acting straight to the right as opposed to up or down any. So I'm just going to adjust the pulley a little bit. Tighten it up. It looks like Stephanie or Grace, you two have the best shot. Can you see the string? Is it horizontal?
Yeah, well, mostly.
All right, what do I need to do? This end go up or down?
Up a little. Yeah. That's better. Yeah.
All right. From the side, can you see it? Does it look horizontal?
Yeah.
All right. I need to figure out how far this thing is going to go. Let's start out on a nice number there. I'm going to start it on 70. And I need to know how far it's going to go before that hits the ground. Because once that mass hits the ground, there's no more driving force. The only thing that's acting on it is friction. So I don't want to include that. All right, so at that point right there, at 13, it is touching the ground. So if I start this at 70, and I'm going to end it at 20. So from 70 to 20, just to make the numbers nice. So I have acceleration. My displacement is going to be from 70 to 20. Negative, well, it's going to go 50. I'm going to make that way positive on this. So 0.50 meters. My initial velocity is gonna be 0 meters per second. I know 3 things, I can find the other 2. What I all really want to know is time. So the question is, how do I find time? Well, Hewitt gives an example. His is in the context of an object falling, but this isn't falling, but the acceleration is constant, and I know how far it's gonna go, and the initial velocity is 0. So if acceleration is constant, and the initial velocity is 0, you got the following formula. Displacement is just 1/2 AT squared. Now, what Hewitt does is, I think he uses height or something like that, and he uses G here because it's a free fall problem. We have an object that's just straight up falling, but it's not falling, but the equation still holds true as long as we use our acceleration. So that's going to be 0.5 is equal to 1/2 of 0.89 t squared. So that's 0.5 is equal to 0.445 t squared. I'm trying to get to t, so I have to get rid of all the other stuff first. So first, let's get rid of the excess baggage of the 0.445. So we divide by it. That's a 0.5 there. So I end up with, on the right-hand side, t squared, and on the left-hand side, 1 point something. .15? 1.2. Now I still want to get t, but I have to undo it. Got that square there, so how do you undo a square? What is the opposite of squaring?
Square root.
So we square root both sides, so t is the square root of 1.12, which is going to be 1 point something.
1.06.
1.06 units?
Seconds.
Yeah. So it should take a little over a second for it to get from here to here. What are the odds? Let me throw my excuses in now. That plays a little wobbly there. And yeah, that is not as smooth as I would have hoped. But I think most of you have a stopwatch on your phone. If you could pull that out. All right, I'm gonna do 3, 2, 1, go. When I say go, I'm going to release the cart. It's going to stop when it hits my hand, stop. All right. 3, 2, 1, go. All right, what are the times?
1.26.
Louder?
1.26.
At 1.30. 1.29. 1.30.
Getting a lot of consistency there.
1.25.
2, 9,
25.
5. Okay.
1.31.
Is that it?
I got 1.3.
1.3? Someone would be kind enough to average up those 7 numbers? Anyone else get the same? Seems on the low side to me, but. Anyone else?
I got 1.29.
Was that a round up or a round down?
Round up.
Round up, and yours?
Mine was right on.
Anyone else? There are 7 numbers there. All right, so we can do this the old-fashioned way. So if I can count 2 5s as my beginning, so I got 5, 11, 16, 20, 25, 26. 26 divided by 7 is just shy of 4. So I think it would be 1.29. You get 1.2856 something.
I got 1.28714.
71. Okay. That one's making more sense to me. Although my gut would have had it higher. All right, so we're off. Why? We've made a prediction of 1.06 seconds and we're getting 1.29 seconds.
Friction from the track, friction from the buoy.
All right. Let's predict how much friction there is. We'll go back over here. Now the only thing that's changing here is that I have 2 forces involved in the motion. I've got the weight and I've got this friction force dragging it back. So I have this weight minus the friction force. And I am assuming that the pulley has negligible friction. And that's going to be equal to 0.55A. That's still the total mass, hasn't changed. So 0.49.